In this lecture, I'm going to show you some ways to calculate the correlation. I expect you to be able to do this manually and conceptually with a small data set. Doing this manually helps you to see where the numbers come from and to understand what correlation truly is. But I also expect you to be able to use SPSS, and then I'm going to show you a quick and easy way to do it in Excel. Not always terribly accurate, but at least it gives you a way to check your work. Let's look first at a positive correlation between two variables. From the last lecture, we'll use the example of age of girls and their height. The X variable is age. The mean or average for the age is 7. The mean or average for the height is 116 centimeters. Notice that if age is above the mean, the height tends to also be above the mean. If the age is below the mean, the height tends to be below the mean. Note too that there is a pattern to the distance from the mean. Let's compare 3 points. Notice that as the data points get further from the mean of X, they get further from the mean of Y. This is an indication that there's a pretty strong relationship between the X variable and the Y variable. Now let's look at the bike helmet's example of negative correlation. The mean or average of the X variable, which is the portion of children receiving free and reduced lunch, is 32.53%. The mean or average of the Y variable is the wearing of helmets. This is 30.88%. Notice that if the X variable for poverty is above the mean, the Y variable of helmets is below the mean. When the X variable is below the mean, the Y variable is above the mean. And once again, we see that the distance from the mean forms a pattern. That pattern is that the distance from the mean shows a really strong relationship. So, to put a number for how the X varies with the Y, we actually get the average of X times Y. This is called the cross product. The problem is that variables have different scales. Think of helmets and FRL, two totally different scales. Think of height and age, again, two totally different scales. So we use z-scores instead of the raw scores for X and Y. Remember that a z-score is simply the score minus the mean and divided by the standard deviation. So the z-score for 50.20% free and reduced lunch is 50.20 divided by 32.53. Oh, let's back up and let me get you some figures up here. Okay, so there's the mean for the free and reduced lunch and the mean for the helmets. This will make a little more sense there with those. Okay, so we're going to look at this score in the X column of 50.20% receiving free and reduced lunch. To get the z-score for that, we're going to take away the mean, we're going to subtract the mean, and then divide it by 0.25, which is the standard deviation. And we end up with a z-score of 0.70. Now let's move over to the Y column and remind you of how to get the z-score. The z-score is, in this case, we take 22.1% wearing helmets minus 30.88, which is the mean, and we divide that by 0.17, the standard deviation, and we get a z-score of negative 0.52. And so on. So we'll put all of those in there. Next, we're going to get the cross products by multiplying the X by the Y. all we do is take the z-score for the x and multiply it by the z-score for the y. Now we add up those cross products and we get a sum at the bottom. This is the sum of the cross products. And finally, we divide the sum of the cross products by the number of data points minus 1 because this is a sample. And we end up with a pretty strong correlation of negative 0.88. There are several other ways to calculate the Pearson R. If you don't have or don't want to calculate the mean and the standard deviation, you can use the raw scores formula. This is not as intimidating as it looks, but once again, you have to do some math. I changed each percent to a decimal just to make this a little more uniform. First, you multiply the x and y raw scores. Next, we're going to square the x's and we're going to square the y's. There's the x's and there's the y's. Now we need to sum up each column. So basically, we need a total at the bottom of each column. Add them up. Finally, we take these values and we replace the variables. You can see from the colors I've put on your screen where each one comes from. The raw scores equation looks complicated because it has all the pieces needed to account for the mean and the standard deviation for each variable. Notice the square root sign, for example, because you want to use the standard deviation, which is the square root of the variance. That's why the z-scores formula is short and easy to remember, but the raw scores formula includes figuring out the mean and the standard deviation for each of these components as you go along. Now we plug the components into the equation and we solve it. And once again, we find that our correlation is a negative 0.88, which is very strong. Now I'm going to show you how to use Excel. It's not always accurate enough for analysis. If you're actually doing some analysis that matters, please do not use Excel, but it's great for checking your manual work. In Excel, you've got your two columns. I've got a column there for the percent of free and reduced lunch, and I've got a column for the percent wearing helmets. Then over in cell C2, you can see I just simply use the Excel formula for correlation, which is equal. Remember, that signals to a spreadsheet that you're using a formula. And then it's CORREL. Then you put in the brackets, we put the first array column, which is A2 all the way down through A13, a comma, and then the second array, which is B2 through B13. And once again, when we hit enter, we're going to find that our correlation is a negative 88.4. And the problem that I've come into there is that I was using percents, and Excel gets a little confused with that. But I wanted to show you what happens when you don't change them to fractions. Now, in SPSS, which is the way that I would always suggest that you figure correlation, the first step is to always set up your variables. Both of these variables are continuous variables, so it's really important in the Variables tab to make note that they are scale measures. When we enter our data, notice that SPSS cannot use percents. I can't leave it as 50%. I have to change it to a decimal, so it becomes 0.50 and 0.22. Now, once we've got our data in there, we go up to the Analyze menu, and you will find Correlate. Then you choose Bivariate because we have two variables. When the window pops open, move the two variables you want to correlate into the variables box. Make sure that the default for Pearson R is checked, and make sure too that the default for indicating significant correlations is checked. They should be because these are the defaults. Now, if you want SPSS to give you the means and standard deviations, you can do that by using the Options button. And when this window pops open, just simply check mark that you want the means and standard deviations and then continue. And now we're ready to click OK. And your output window will open. We're going to take a closer look at what you get. First, you get the mean and standard deviations that you asked for in the options. You can see that the mean for free and reduced lunch is 32.42%, and the mean for helmet wearers is 30.75% of the students wearing helmets. And you see that the standard deviation for free and reduced lunch, percent of free and reduced lunch, is 0.25, and the standard deviation for the percent wearing helmets is 0.17. There is more variability in the percent of students receiving free and reduced lunch help at the schools than there is variability in the percent of bicycle riders wearing helmets. Next, you get the correlations table. Let's look at how to read it. Look across the row for free and reduced lunch, and you can see that the Pearson R is the first column click gives you the correlation with free and reduced lunch. Well, the correlation of any variable with itself is complete correlation or 1. That information is not useful. Now look over to the column for helmet wearers. Notice that you now have the Pearson correlation . Sorry about that. You now have the Pearson correlation between the two variables, which is, surprise, negative 0.883. The next row just reverses it, showing the Pearson correlation between helmet wearing and free and reduced lunch help. But that kind of is nonsense because we wouldn't think of helmet wearing really preceding free and reduced lunch help. There's some other really important information in this table. First, notice the significance, which is two-tailed. This indicates that there is less than a 1% chance that these results are simply by chance. We'll look at significance later, but for now, please understand that there is less than a 1% chance of this relationship being just random. You can have a great deal of confidence in these results. Once you've found the correlation, you report the information. One suggestion would be, a strong correlation was found between the student poverty rate, measured as a percent of students receiving free and reduced lunch assistance, and the portion of students wearing bike helmets. R equals negative 0.88, P less than 0.01. When poverty rates were higher, fewer students wore bike helmets. When poverty rates were lower, more students wore bike helmets. Notice that I included the significance as a p-value. More on that later. I also chose to describe the correlation, which would be very typical. To just give numbers doesn't help your reader. You want to make sure your reader understands the relationship here between poverty and bike helmet wearing. This has been a lot of information. Go back through it if you got confused at any point. Then try the practice problems. I'd suggest that if you want to really be confident, you work each problem out by hand, with Excel, and then with SPSS. With spreadsheets so ubiquitous, I can imagine that many folks actually calculate correlations by hand. However, doing so, especially with the z-scores, helps you to conceptualize what you are doing. Correlation is often expressed as Pearson, and it's the average of the cross products. The cross products, remember, are simply one variable times the other variable.